In the previous section, we learned what a differential equation is, just some equation that involves a derivative, and the solution of a differential equation is the function, usually we use the letter y, that actually make the equation true. So in section 1.2, we're going to learn about initial value problems. So an initial condition on a differential equation is just some specified point that must lie on that solution curve. We know that antiderivatives are not unique. There's always that plus a constant, which essentially corresponds to a vertical shift. So you can shift the curve vertically, but once you know a single point, you've got a unique solution. So if you have a differential equation together with an initial condition, it's an initial value problem. So we're going to go back to the problem that we came up with last time. There was a bank account where it was, let's see, gaining 10% of its value, but also losing 10,000 a year. And then the m values were given in thousands. We came up with this differential equation, which we see right there. And we now want to turn it into an initial value problem and come up with a full solution. So we needed a differential equation and an initial condition. And if we have $90,000 at time t equals 0, that's our initial condition. So we'll write m of 0 equals, and it'll be 90 because m is in thousands. All right, so how do we solve the differential equation? Well, we're going to get the m's on one side, the t's on the other side, and then we're going to integrate. All right, so to start off with here, let's see, I know that dm over dt equals, and just to make this a little cleaner, I'm going to factor out the 0.1, and that leaves me with m minus 100. Okay, then when we get the m's on one side, the t's on the other side, so we separate the differentials. All right, so dm, we actually divide by m minus 100, and that equals 0.10 dt. Okay, so now we're ready to integrate both sides. So this implies that the antiderivative of this left-hand side will work out to be the natural log of m minus 100. We actually need absolute values on there, but we're okay. So we take an antiderivative on this side, we get 0.10 t, and then we add in our constant. Okay, so now we're trying to solve for m, so we exponentiate. So we have m minus 100 equals e raised to the 0.10 t plus c. Okay, which I could maybe rewrite as e to the 0.10 t times e to the c, or e to the c is just some other constant, so I'm going to call it k times e to the 0.10 t. All right, so now, well, that's m minus 100. M would be 100 plus k times e to the 0.10 t. All right, so there is what m is, but we haven't yet solved for k. That doesn't do any good to know how much is in your bank account multiplied by an arbitrary constant. We actually have to figure out what k is. So we replace m with 90, and we replace t with 0. When we do that, we end up with 90 equals 100 plus k, so that implies that k should be negative 10. Aha, so we've managed to come up with our solution. So m, try that again, m equals 100 plus, oops, not plus, I can use a negative, minus 10 times e to the 0.10 t. There is the solution of our initial value problem.